Welcome to my video lecture. Star Electrical Machine Tool Paper Code PCPT 501. Today's topic is MMF method and ZPF method or zero power factor method. Myself, Kubun Banerjee, Assistant Professor of Electrical Engineering Department, Dr. Sudhir Chandrasekhar Institute of Technology and Sports Complex. This institute is previously known as Dr. Sudhir Chandrasekhar Institute of Technology and Sports Complex. This institute is previously known as Dr. Sudhir Chandrasekhar Degree Engineering College, and it's under JIS Group. Today, we will discuss about MMF method or magnetomotive force method. Basically, this method is known as ampere turn method. The synchronous impedance method is based on the concept of replacing the effect of armature reaction by a fifth reactance. And here, the MMF method replaces the effect of armature leakage reactance by an equivalent additional armature reaction MMF, so that this MMF may be combined with the armature reaction MMF FAR. This FAR is basically the additional armature reaction MMF, and which is combined with the original MMF. Now, some informations are required to predict the regulation by MMF method. Those are: synchronous machine should produce sufficient MMF so that it can generate terminal voltage. Also, this produced MMF should be sufficient to overcome the armature reaction and leakage reactance flux. Thirdly, the resistance of stator winding per phase. Fourthly, open circuit characteristics at synchronous speed and short circuit characteristics. The following information also required to predict the regulation by MMF method. Among those I have already mentioned, and among those the most important two things are the resistance of the stator winding per phase, open circuit characteristics at synchronous speed, and thirdly, short circuit characteristics. This method makes use of phasor diagram of magnetomotive forces. The following procedure is used for drawing the phasor diagram at lagging power factor. So let us draw the phasor diagram. Here, the armature terminal voltage per phase G is taken as reference. Okay. So, this is O and this is A, and this OA axis is basically the terminal voltage V, and this is taken as reference. Secondly, the armature current phasor IA is drawn lagging the phasor V for lagging power factor angle phi. Now this IA, this IA is drawn as lagging power factor when the angle is phi A. So we have pointed out OB. OB is the axis. Here we have drawn the lagging current phasor. Thirdly, the armature resistance drop IAR is drawn in phase with IA along the line and join O A and C. This is IA array drop. This one you see is the IA array drop. Now from OCC, the field current IF dash corresponds to the voltage of E dash is noted. This is the IF dash voltage. Here, this is the IF1 voltage or IF dash voltage corresponding to the voltage of E dash. We have drawn this IF dash with 90 degree lagging position than E dash. Now from OCC, the field current IF dash corresponding to the E dash is already drawn. Now draw the field current IF dash leading voltage E dash by 90 degree. It is assumed that on short circuit, all the excitation is opposed by MMF of armature reaction and armature reactance. Thus, IF1 or IF dash is IF angle 90 minus alpha. From SCC, we have drawn, this is the SCC curve here. You can see here. Determine the field current IF2 required to circulate the rated current on short circuit. This is the field current required to overcome the synchronous reactance of IA excess. Now draw the field current IF2 in phase opposition to IA. Thus IF2 is IF2 angle 180 minus 5. So this is the IF2 we have drawn, and which is 180 degree phase opposition to IA. So you can see that IF2 is just 180 degree phase opposition to IA. Okay. And IF which produces the sufficient flux to overcome the armature reaction and also produces terminal voltage. So the voltage definition we are getting here, I naught minus V divided by mole divided by G into 100%. Okay. So here we have taken all these points in the IF versus open circuit voltage, and we have put out the value. We have drawn the curve of OCC and SCC, and in this position we have put that the IF current and corresponding voltage in OCC current, that is V0, and IF1 the corresponding EMF is E dash, and IF2 corresponding current in short circuit, that is IA. That's what we have drawn here. MMF method is optimistic method, and here it gives less value than the actually generated EMF. So, the phasor diagram at power factor cos phi, we are neglecting RA, and this is the curve where we have neglected armature resistance RA, and this curve is drawn. And here IF2 is IF2 angle 180 minus 5. IF dash is IF dash angle 90 degree, and IF is combination of IF dash plus IF2. So in that way we can write it. Now we will go to zero power factor method or ZPF characteristics. The zero power factor characteristics of an alternator is a curve of armature terminal voltage per phase plotted against the field current obtained by operating the machine with constant rated armature current at synchronous speed and zero lagging power factor. And this is known as Portier triangle method. Now, for maintaining very low power factor, alternator is loaded by means of reactors, and alternatively and by an underexcited synchronous motor. The shape of ZPFC is very much like that the OCC displayed downwards and to the right. The phasor diagram corresponds to the zero power factor lagging load is shown here. So, we know that the terminal voltage V is taken as the reference phasor. At zero power factor lagging, the armature current IA lags behind the voltage V by 90 degrees. And we are getting that V plus IARA plus IAXAL equals to EG. At normal condition, a flux created phi F. Now at loaded condition, IA will flow and phi AR armature reaction flux created, which is opposite of phi F. So the resultant flux phi R will be developed, and this is EG equals to V plus IAXL. So it is seen that the terminal phase voltage here, this one, the terminal phase voltage here, the reactor's voltage drop IAXAL, this one, and the generated voltage EG all are in phase. Okay. All are in same phase. Therefore, V is practically equal to the numerical difference between EG and IAXAA. That means we can write it V equals to EG minus IAXAA. Now we will develop the Fourier triangle. From here we can get the armature phase reactance and armature reaction from these characteristics. Consider point V on the ZPFC correspond to the rated terminal voltage V. This is the V point. And field current is ON. This is O, and this part is O. Now ON equals to IF equals to AF by TF. If this is the condition of operation, the armature reactance MMF has a value expressed in equivalent current, that is Ln equals to IAR equals to FAR by TF. Here this is AF. The field current will result in a generated voltage from a no-load saturation point. Since the lagging zero power factor operation G equals to V plus IAXAA, the vertical distance must be equal to the leakage reactance voltage of IAXAL, and from there we can write that XAL equals to voltage per phase divided by rated armature current. The effect of field linkage flux in combination with armature flux given rise to an equivalent leakage reactance studies. XF, known as Portia reactance, XP. This is XP. Portia reactance. Can write that XP constant voltage drop off is divided by ZPF rated armature current per phase. So from here we can draw the phasor diagram, and this is the for cylindrical rotor machines having Portia reactance XP is approximately equal to leakage reactance XL. In cylindrical machine, XP is large 3 times in XAL than XAL. Here we have drawn this phasor diagram using this following method, where V is the terminal phase voltage at full load. It is taken as reference phasor and drawn horizontally. IA is the full load current lagging behind V by an angle phi, and cos phi is the power factor of the load. Then we have taken the voltage drop IARA in the armature resistance, if we have considered, it is drawn parallel to IA. Then IAXAL, the leakage reactance voltage drop, it is perpendicular to IARA. Then we have joined all this together and it represents the EMF EG. For field excitation current IR corresponding to the generated EMF EG drawn from open circuit characteristics. And the percentage voltage regulation, we have determined that EF minus V divided by V into 100. That is about its method. And here the factor is that it is not necessary to plot the entire ZPFC for determining XAL and FA experimentally. Only 2 points we have taken that here, which is this B and this is B dash. These 2 points are sufficient. Point B corresponding to field current, which gives rated terminal voltage, while the ZPF is adjusted to draw the current. The point B dash corresponds to short circuit condition, where V equals to 0. The point B dash corresponds to short circuit condition on the machine. Thus, OB dash is the field current required to circulate the short circuit current equal to the rated current. So in that way, we can draw these points assuming some conditions, and we have drawn this Portia triangle. And following assumptions are generally taken to draw the potential triangle meter. 1. The armature resistance array is neglected. Secondly, the OCC taken on full accurately presents the relation between MMF and voltage on load. Thirdly, The leakage reactance voltage IAXL independent of excitation. And fourthly, the armature reaction MMF is constant. That means we have actually four conditions for drawing the phasor triangular pattern. First one is armature resistance RA is neglected. Secondly, OCC taken on no load accurately represents the relation between MMF and voltage and load. Thirdly, the leakage reactance voltage IAX is independent of excitation. Fourthly, the armature reaction MMF is constant. And all these parameters are taken into consideration while we are drawing that phasor triangle. And this Fourier triangle method is very, very important for calculating the voltage regulations. And in general, three methods are there. All three methods I have covered related to voltage regulation of the issues. And first one was that EMF method. Second one, MMF method, and third Fourier triangle method. And in synchronous machine, as the synchronous machine can operate from lagging to leading power factor, so the voltage regulation is very important part of the synchronous machine. And definitely we can do it very properly with this following test of open circuit, short circuit, and this resistance test. And all these three methods, EMF method or MMF method or ZPF method, these methods are very, very helpful for calculating this voltage regulation of synchronous machine. So not much more for today's class. Thank you all. You can go through the book of train of electrical methods. And also you can follow the book of JD Gupta of electrical machine, or you can go through Mathur Kothari in this weekend. So thank you all for listening my lecture.